Hello dear students. In this session we are going to study different measures used to understand a network. For example, in the social network we may want to know who is more influential, who interacts more and who is similar to whom. So here the plot as an example related to measuring influence. So it is difficult to measure a influence. So measuring influence is not as simple as counting the number of friends. A person may have many connections, but that does not necessarily mean that the person is highly influential. So we need mathematical measures to identify influence in a network. So why do we need measures? Uh, so there are three important questions. Who are the central or influential individuals? What interaction patterns are common among friends? Who are the like-minded or similar users? These lead to different measures, which is centrality, reciprocity, transitivity, balance and status, and similarity. So before analyzing a network, we need suitable measures to quantify these properties. So the first one is centrality. So the centrality tells us how important a node is within a network. For example, in a social network, if we want to find the most influential person, we can use centrality measures. So centrality based on connections. One simple way to decide whether a person is important is to look at the people connected to that person. For example, A tends to B, C, D, E. A has many connections. So A may be considered more central than a person having only one connection. This leads us to a degree centrality. So the degree centrality ranks nodes with more connections higher. If a person has more friends, that person gets a higher degree centrality. A has 8 friends, B has 3 friends, C has 5 friends. So then A will have the highest degree centrality. So the degree centrality example, here look at the graph. Here the V3 have 5 degree. So another nodes have lower degrees. So the node with degree 8 has more direct connections and therefore receives a higher degree centrality value. So degree centrality in directed graphs. For example, A tends to B means A is pointing to or following B. There are two important measures, in degree and out degree. So we use the in degree plus out degree is the combination, but in degree is mostly used in practice. So that the out degree tells us how many links are going out from a node. A tends to be C, D. Therefore, out degree of A equal to 3, which means A has 3 outgoing links. So the normalized degree centrality. So raw degree tells us the number of connections, but sometimes we want a value between 0 and 1. So that different networks can be compared. So that we are using three ways: maximum possible degree, maximum degree, and normalized degree sum. So these are the formulas. Di is the in degree, di by n minus 1 is the normalized degree, di by max I degree is the max degree, and sum is the di by n. So that the maximum possible degree is n minus 1. So the next one is degree centrality for directed graph examples. Here we are having the nodes A to G. So the nodes A to G is represented in the first column. The degree of each node is here. Second column, and then the third column. Out degree of each node is here. The centrality is 1 by 2. And the rank is 1 by 2. The rank. Like this we will represent the rank. So A degree is 1, out degree is 2. So we get the value 1 by 2. eigenvector centrality. So now we will move to more intelligent measure. Having many friends does not automatically mean that you are important. Suppose A has 10 ordinary friends while B has only 3 and influential friends. B may actually be more important. So eigenvector centrality considers the importance of the numbers. So next one is formulation. So a node should receive a high centrality value in important neighboring nodes point. For example, important A tends to B. If A has a high centrality and B and points to B receives a stronger contribution. So the need for normalization. So if we simply if keep adding the centrality values of numbers, the values can become very large. So we need to normalize the values so that we are introducing the value constant lambda, leading to the eigenvector equation. So eigenvalue and eigenvector. So the centrality vector becomes an eigenvector of the adjacency matrix and the corresponding value is the eigenvalue. In simple terms, A is equal to lambda x. For A is the adjacency matrix, x is the centrality vector and lambda is the eigenvalue. So that now the equation is lambda c equal to A per t c. C is the eigenvector, A per t is the adjacency transpose adjacency matrix. Lambda is the eigenvalue. So finding the eigenvalue. Instead of solving everything directly, we can use an iterative. Start with an initial guess. For example, gives every node a central eigenvalue and repeatedly update the values. This is the power method. So the first one is initial guess is CE of 0 and we will do for d iterative times. So we can write C of 0 as a linear combination of eigenvectors VA of the A part T. So in the next calculation, we are moving towards the lambda 1, lambda 2 type base. We are applying for T iterations. As the number of iterations increases, the contribution associated with the largest eigenvalue dominates. So eventually, the resulting vector approaches the eigenvector corresponding to the largest eigenvalue. So lambda 1 is the largest eigenvalue. As t grows, we will have in the limit c of t, alpha 1, lambda 1 per t and v1 are equivalently a per t c of t equal to a per t c equal to lambda 1. So the final eigenvector centrality, compute the eigenvalues, select the largest eigenvalue, find its corresponding eigenvector. The components of that eigenvector represent the eigenvector centrality. So eigenvector centrality. So to compute eigenvector centrality of A, we follow these steps. So eigenvector centrality examples. So A adjacency matrix is 0, 1, 0, 1, 0, 1, 0, 1, 0. So now we calculate the equation lambda c equal to ACE A minus lambda I CE, which is equal to 0. So determinant of z equal to 0. So we are calculating the eigenvalues. So minus root to 0 plus 2. The largest eigenvalue is plus 2. So here we are applying which is equal to G. So that C equal to 1 by 2 root 2 power 2 1 by 2. So this is the largest eigenvalues. So this is the example of lambda value and also centrality eigenvalues. So the next one is card centrality. So centrality only passes through outgoing edges. In some directed graphs, particularly directed acyclic graphs, a node centrality can become zero, even though it has many connections. Simple example, A to B to C. C may have several incoming relationships, but because the direction of propagation is important, the basic eigenvector calculation can produce undesirable zeros. So that we are using the bias term in the card centrality, which is beta. To resolve this problem, we will add the bias beta. So card centrality of VA equal to alpha summation I equal to 1 to n A j comma I C card centrality of Vj plus bias. So the centrality equal to network contribution, which is in the previous method. Here the centrality equal to network contribution plus bias. So this is the eigenvector centrality plus the bias. So this is the hard centrality. So then here we are using the alpha value. So when alpha equal to 0, the eigenvector component disappears and all nodes receive the same centrality. As alpha becomes larger, the influence of the bias term becomes smaller. So alpha controls how much we trust the network connections. Smaller alpha, more effect from the bias. Larger alpha, more effect from the network structure. So the condition on the alpha. In practice, we select alpha based on the largest eigenvalue so that the calculation remains stable. So alpha less than 1 by lambda, where lambda is the largest eigenvalue of a power t. So chord centrality example. Here the eigenvalue is minus 1.08, minus 1.0, minus 1.0, 0.35, 3.32. So the lambda max is the 3.32. So that alpha equal to 0.25, which is less than 1 by 3.32. So here we choose alpha is this 0.25, which satisfies the required condition. So the resulting graph shows the most important